You have fallen into Event Horizon with John Michael Godier. John is joined by Dr. Martin Cordiner. Dr. Martin Cordiner is an astrochemist at NASA's Goddard Space Flight Center and a research professor at the Catholic University of America. His work focuses on the chemistry of comets, interstellar clouds, and planetary atmospheres, with special emphasis on what these environments can reveal about the origins of stars and planetary systems. He is the lead author of the recent study JWST detection of a carbon dioxide-dominated gas coma surrounding interstellar object 3I Atlas.
Dr. Martin Cordiner, welcome to the program.
Thank you very much, John. It's a pleasure to be here.
Now, Doctor, we have run into, or it ran into us, one of the most interesting astronomical developments in the last decade, which is saying a lot because we've already seen two interstellar objects so far. One very enigmatic, and the other one not so enigmatic, but interesting in its own right. And now we're on 3I Atlas, the third confirmed interstellar object. And it is definitely interesting in that it is the oldest thing we've seen other than the universe itself. This thing it could be, based on its motion, statistical evidence, could be 7 billion years old from an earlier time period in the universe. And that begs a question you have to ask. What was the chemistry of the Milky Way like back then? And 3I Atlas has a chance of telling us that. What have you found so far in the short time that everybody's been studying 3I Atlas, which has only been since, early July, something like that? What have you found about the chemistry, and what is it doing that deviates from a solar system comet, a run-of-the-mill Oort cloud object?
Yeah, well, as you say, this is a really fascinating object. A fascinating time to be alive, that we can bear witness to the passage of these interstellar objects through our solar system and be alive in the era where we have access to incredibly powerful telescopes on the ground and in space to observe these objects, find out what they are, where they came from, and what they're made of. As you say, it's fascinating to think back to where these objects came from, what environments they formed in, what the conditions were like in those environments. What we're looking at here with this interstellar object is basically one of the oldest fossils that we've ever seen, a fossil that contains a chemical record, if you like, of its formation environment and the conditions it was exposed to during its travels around the galaxy for the last, as you say, several billion years. Now, we have to be a bit careful when we talk about the age of this object because we don't have access to sort of isotopic samples that we might be able to put through a laboratory and do an accurate age dating, right? And as far as I know, no isotopic ratios have been derived for this object that might give us real robust evidence of its age. So we have to look to sort of indirect evidence to understand how old it is. And the strongest evidence we have comes from comparison of its trajectory with models, with dynamical models for how these objects move throughout our galaxy and how they move through time and trace their trajectories back to a likely origin site. And so there was an interesting study by the Otautahi Oxford group who have constructed a very detailed model of how these objects move in our galaxy to trace back the trajectory of this object, 3I Atlas, and determine that it, with a good probability, that it comes from a part of the galaxy that seems very old in terms of the ages of the stars there. And that's this so-called thick disk population. It's a population of stars within what you would call the plane of our galaxy. Our galaxy is essentially like a plate kind of structure, mainly composed of a disk. But there's this thick disk population of stars which are moving around a bit faster that we call kinematically hot population. They're moving throughout this disk in a more excited way than the stars in the plane. And this population, this thick disk, could be almost as old as the universe itself. These are some of the oldest stars in our Milky Way galaxy, potentially as old as 14 billion years. And so if we trace back the age of 3I Atlas to this population, if we link it to that population, then what this means is that it could be as old as some of those stars, and the estimates that I've seen potentially place it within an age range of 7 to 14 billion years. So that is, it's incredible to think that we have passing through our solar system one of the oldest objects, potentially one of the oldest objects in the universe. And we get a chance to point our telescopes and find out what it's made of, and get a direct window into the conditions of the system where it formed. We believe it formed probably in a similar way to the comets in our own solar system, which means accreting during the process of planet formation as gas and dust clumps together, if you like, to form these icy, rocky, small bodies which progressively grow larger and larger, and some of them eventually become planets. A lot of them don't grow larger and larger. There's a lot of these smaller objects flying around when planets are being formed within the disk of a young star. And we presume that this is what was happening. We observe these disks around young stars throughout our galaxy, and this is how we believe planets form throughout the galaxy, and also comets. So these kinds of objects are forming in these environments around these very old stars in the thick disk, getting ejected out, and some of them end up passing after billions of years through our own solar system where we can observe them. So that gives us this window back in time. And so we measure the chemical compositions through spectroscopy. We have many different wavelengths that we can study throughout the electromagnetic spectrum, all the way from gamma rays and X-rays and ultraviolet through optical and infrared and radio. This is sort of a library of tools we have at our disposal to investigate chemical compositions of these objects as they heat up and start to release the gases that they've been storing inside for however many billion years. So it's just a case of reading the spectrum then to work out what it's made of. And that's what we've been doing. Astronomers around the world have been pointing their telescopes at 3I Atlas. We've been using our best space-based assets. It's an all-hands-on-deck approach. It's you can think of it as a once-in-a-lifetime opportunity to observe an object such as 3I Atlas. We see that these objects come along every now and then. This is the third interstellar object. There are likely many more. We have no guarantees. This is an unusually bright object, actually. It's brighter than Borisov. It's brighter than Oumuamua. There's no guarantee we'll get another interstellar object this bright. So it's all hands on deck and all telescopes on the sky to point at this object and work out what it's made of. So what did we find? That's something that we are addressing with our current studies, and I just submitted an article to Astrophysical Journal Letters on the composition of 3I Atlas as studied by the James Webb Space Telescope, and we have beautiful infrared spectra of this object. It was a short integration on the sky, a short observation, just a preliminary reconnaissance of this object just to get a first inkling of what it is and what it's made of, and some of its properties, so we can follow up a bit later when the object is brighter. This is just our first try, and what we saw was just amazing. The amount of carbon dioxide, CO2, in this object's atmosphere. I refer to the gases coming out of the object as an atmosphere or a coma. The coma is the typical nomenclature that we describe these gases with from a comet. There's no reason to assume this is a comet a priori as it's coming in. We don't know much about it at all. But from our observations, it seems very comet-like. It produces a dust scattering of optical light surrounding the object as a result of interaction of the dust in its atmosphere with the solar radiation. So that was the first evidence that it has a coma. And then we see some of the gases it's producing. And with the James Webb Telescope, we were able to see, as I say, very strongly the carbon dioxide. We also picked up fainter emissions from carbon monoxide. And then fainter still was the water emission, H2O, water vapor. And so we're starting to build up a picture of what it's made of. And these are the typical gases that you see in the comets that we all know from our own solar system, comets like Halley, Hale-Bopp, 67P, Churyumov-Gerasimenko. There's a lot of comets with unusual names, and we see them every year, and we build up an idea of what they're made of, and kind of performing chemical surveys of these objects. And just time and time again, when we observe these comets from our own solar system, we see these gases which seem to be coming from the sublimation of solid ices inside the nucleus. As they heat up, as they get heated by the sun, these gases come out, form a coma or atmosphere, and then we observe them. So 3I Atlas, back to your question, John, very CO2 rich, surprisingly water poor. What this then translates to is a high CO2 to water mixing ratio. And when we compare that to typical comets that we observe from our own solar system, that CO2 to water ratio is one of the highest ever seen in a comet. In fact, it's the highest ever seen within the distance range from the sun between 3 to 4 astronomical units where we observed this object. We can talk a little bit about the variation of that ratio with heliocentric distance and how it's supposed to behave. You know, this water abundance, this low water abundance and high CO2 abundance, that's likely to change as the object evolves and gets closer to the sun, because water has a different set of physical properties to carbon dioxide ice. Water ice doesn't like to sublimate or enter the gas phase as easily. It takes a higher temperature to produce water vapor from water ice than it does CO2 vapor from CO2 ice. So we can envisage that as this object's coming in, it's not very active when it's far from the sun. It came in from, of course, parsecs, light years, thousands of light years away, and it's come all the way to approach our sun and start to heat up, and these ices start to sublimate. And the first thing to sublimate is the carbon monoxide. In terms of the things we observe, carbon monoxide, CO, is very volatile gas. It likes to leave the ice phase very quickly. As soon as the ice heats up above about 20 or 30 degrees above absolute zero, that CO ice starts to enter the gas phase. And then as the comet approaches the sun more, the CO2 starts to be released. And then one of the last volatile species to be released from the nucleus is the water. So we think that there's probably an element of that going on. And as the object 3I Atlas approaches the sun closer, that water production rate is probably going to start coming up, and the CO2 to water ratio is therefore going to come down a bit. But we think that compared to the other comets we've observed from our own solar system, if it behaves in a similar way to those, even when it gets close to the sun, this object has so much CO2 coming out of it, we think that it's still going to look very CO2 rich. So even accounting for this temperature and distance from the sun variation, this still looks like a chemically unusual object.
Now, in regards to the carbon monoxide and how there's not a lot of it, let's take that one first. Could that indicate that the object passed semi-close to a star system in the past at some point in its history and it got depleted? Or did it get depleted when it was, before we even discovered it, when it was coming in? Is it that volatile to have depleted its carbon monoxide before we ever even saw it?
This is a fascinating question. It gets into issues of the nature of interstellar objects. How much of the different chemicals and ices do they contain? What was their intrinsic inventory? Did they come from an environment that was rich in those gases? Could they have been then lost? If we think about Oumuamua, we didn't spectroscopically detect any gases coming from Oumuamua, the first interstellar object. And some of the theories to explain a lack of outgassing from what should be a cold, icy object is that, well, maybe it passed close to a star on its way. Maybe it got heated when it was being ejected from its host system. Maybe it had a close encounter with another star in its host system that meant that some of that intrinsic chemical inventory, such as the more volatile species, carbon monoxide, methane, maybe they ended up getting sublimated away before it even arrived here. maybe there was chemical processing happening within the body during its passage. That's another really intriguing thing to study from a laboratory astrochemistry perspective. You could irradiate these sorts of ices in the laboratory and see how much of them survives and how much of it gets turned into something else, how much of it gets sublimated, and then that's the sort of experiment you can then do to compare with the chemical inventories that we observe and see if they are changing in the way that we might expect, or if we can predict some of those chemical changes that might be occurring, and then compare those to observations to try to validate our theories. So, but just going back to your question about a relatively low amount of CO. So, we see a CO to water ratio in 3I Atlas of greater than 1. I think it's about 1.4. So a little bit more CO than water. And from a global cometary science context, that's actually fairly CO rich. So we have to bear in mind that at the present time, it seems like there is a pretty decent amount of CO in this object. But again, as it approaches the sun and the water comes more active, the CO2 is unlikely to become more active. And so it may end up, as you say, showing evidence of being CO depleted in that case.
Now, in regards to the object, so, all right, it comes in, and we're looking right now at its profile on its way in. Then it, hits perihelion, and maybe we can study it with some Mars probes and things like that when we can't see it. It's behind the sun. And then it goes on its way out. How do comets overall change? At least with solar system, we haven't seen what this one will do yet, but with solar system comets, how do they change, chemically speaking, on their way out versus what they looked like on their way in? Well,
as comets pass through the solar system, most comets that we observe with our telescopes and even with our eyes as they come through the sky and light up, they're passing pretty close to the sun, and the amount of solar radiation that they're receiving on their surfaces increases, with the 1 over distance squared rule. So as it gets closer to the sun, the heating increases with the inverse square of the distance from the sun. So the heating really ramps up the closer the object gets. And as a result of that, a wave of heat from the surfaces of comets are fairly dark, a bit like the moon. They may appear shiny, but in fact, they have a low albedo, which means they absorb a lot of sunlight. And so this thermal heating on the surface proceeds inwards and starts to heat the ices that are stored inside. Those ices sublimate, come out. We see them as plumes and an outgassing. And then as the comet comes past perihelion, it's closest to the sun, the heating, of course, peaks there and the activity peaks. And as the comet starts to move away, there's sort of a thermal inertia effect that we sometimes see, that even though it's moving away from the sun a little bit, it's still receiving heat, and it can still be heating during that stage, even though it's moving away from the sun, because it's still receiving heat, and there can still be a net heating of the nucleus. So as that comet then proceeds to move further away from the sun, the heating decreases, the cooling increases, it radiates its heat to space, and ultimately the sublimation starts to decrease from the inside out. So the inside will start to cool before the outer layers. And so if there's more water in the outer layers, because it's less volatile and kind of sublimated less overall, then you may see an increase in the water and a decrease in the other gases during that period. But it's quite complex and depends on the intrinsic structure of the nucleus. And so as it cools, we expect to see changes again in the chemical compositions. And interesting effects can happen as an object sort of rounds the sun in terms of seasonal effects. You think of a comet, you think of a rock, an icy rock moving through space. You don't sort of immediately think of them as sort of seasonally varying objects. We know planets have seasons depending on their polar tilt. Well, comets can have seasons as well. They spin, they have an axis. If that spin axis is pointing towards the sun in its north. As it approaches the sun, then of course we'll have more heating in the north, and that could get depleted of volatiles, depleted of ices, such as the water and the carbon dioxide and the carbon monoxide and other ices that may be present. And then as the object rounds the sun, it might point a different side, a different part of the comet may come into sunlight. And so then we could see fresh sublimation of material that wasn't previously being heated. So things can change significantly during that process. And
it's gonna be fun, actually, because I've seen comets before, going all the way back to Hale-Bopp back in the 90s, observing that with, in my amateur capacity. And yeah, they can flare, they can do all kinds of interesting things as their conditions change. And this might do that. I don't know if it'd ever go too crazy, but still, it's really interesting to get that profile along the whole passage of the object. Are you happy with the amount of observations being done? As a scientist, do you think that the data set that we're getting on this object is as robust as we could be doing?
I'm a scientist. I always need more data, John. There, in my opinion, there should be no limit to the amount of data we should be obtaining on this unique and very special object. Having said that, I'm but one scientist among a global network of astronomers studying many galaxy collisions, dark matter, star formation. So there's many different competing topics to use our telescopes for. We live in an amazing time of astronomy with access to so many amazing and large and powerful telescopes to observe all these phenomena. But we are limited in the amount of funding that we can request and be granted by government funding agencies or various kind donors, people who want to build telescopes and provide money for this sort of thing. So I'm going to say, we definitely would benefit from more, but for the time being, I would say I'm suitably impressed with the amount of attention Atlas is getting from the global media and from the global astronomical community. Everybody in planetary science, for sure, is fascinated by this object and watching it with bated breath to see what it's doing next. In telescope time, we don't just go and knock on the door of one of these big telescopes and sort of tell the operator what to point at, or make friends with him, buy him a beer, and pass him the coordinates of what we want to see. It's a very strict and tightly governed process, subject to intensive peer review, and so it's a little, you could say, the wheels sometimes move a little slowly, and so what that means is that we may have to put in applications for telescope time that have to be vetted by the standard procedures and then peer reviewed by other scientists to allow us to actually get these data sets and to do more and more observations. So right now, we're writing our telescope proposals, observations, and we have to be hopeful that the people that review them grant us that precious telescope time so that we can carry on observing 3i Atlas in the best way. Now, I'm also aware of coordinated efforts to use various space assets to observe 3i Atlas. It's such a unique object that NASA, with all of its space hardware, is orchestrating a plan to get as many different instruments from as many different pieces of space hardware and interplanetary missions as possible to observe this object during the short amount of time we have. Part of the issue here is the fact that the object in question, 3i, is traveling fast and travels past the sun when the Earth is on the other side of the solar system to the object. So it's not going directly behind the sun as we observe it from Earth. It's on sort of a tilted orbit as it comes in. But it's basically in a part of the sky which makes it very challenging to observe from Earth and using any telescopes around the Earth. And so that closest approach to the sun happens October 29th, just a month and a half or so from now. And the fact that it's so close to the sun means that, we're going to struggle to observe it, and we're going to struggle to monitor it using ground-based hardware. So we have to look to space-based hardware, and there is indeed a large number of space missions flying to various planets. We've got Juno at Jupiter. We've got Maven and MRO at Mars. We've got various hardwares at Mars. There's numerous rovers and orbiters around Mars at the moment, which will be able to do a much better job of observing it close to perihelion than we'll be able to do from Earth. So it's incredible to think about this orchestrated effort going on through from around the solar system to get what we can on this object. From that perspective, I'm confident that we'll be able to be monitoring it with sufficient regularity and sufficient wavelength coverage that if this object does do something unusual or surprising, even if it doesn't do something unusual or surprising, it's still important to measure that. And measure is certainly going to change and evolve as it passes. And so, yeah, it's crucial that we have these plans in place to keep on monitoring it as it carries on and continues to provide a source of intrigue for astronomers.
Now, formation temperature. So could it be that where this object formed within its star system of origin could be defining the chemical profile that we see? In other words, can they differentiate? I mean, with a very, very small object like that, where maybe the water is simply deep inside of it, as opposed to near the surface where it can be warmed and sublimate, whereas the carbon dioxide and monoxide are shallower. Can that actually happen? Or am I completely all wet and that it wouldn't do that?
Well, we don't know how big this object is, right? There are some estimates, some initial estimates, which didn't take into account the fact that it had a coma that was making it seem brighter. Initial estimates said it could be a few tens of kilometers in size. More accurate measurements that try to subtract off this bright, dusty coma and therefore leave the signal from the nucleus are showing us that the nucleus size is less than a few kilometers in radius, less than about 3 kilometers in radius. Nevertheless, that is, that's small on an astronomical scale or on a planetary scale. But with an object of that size, you get into a realm where things are starting to differentiate. And the reason is that the heat doesn't penetrate very quickly into the nucleus. It's quite a porous sort of physical structure, kind of almost maybe sponge-like. And we know this from the visit of the Rosetta mission to Comet 67P and also the gathering of cometary dust samples from other sample return missions to space. We know the density of comets is very low, and because of that low density, heat doesn't easily penetrate inside them. And what that means is that even if the comet experiences significant heating from the outside, the heat doesn't penetrate that far. However, if the heat penetrates a little way, say a meter or a few tens of centimeters, then you would expect the preferential loss of the more volatile ices from those surface layers. So the closer to the surface you are, the more likely you are to lose those volatile species. And so you may end up with more water-rich layers closer to the surface because water is the less volatile. This is greatly simplifying the complex thermodynamic theory and thermochemical calculations that you would have to do to really determine how the interior chemical abundance structure changes with time and with heating rates. So it's broad brush, but yes, I believe that it would be possible to end up with a differentiated body. You talked about differentiated bodies in general. We're talking about maybe part of the object being CO2 rich, part of it being water rich, maybe part of it's rich in organics, or other ices like maybe ammonia, methane, something like that. And we see this kind of chemical differentiation happening on other small bodies in our solar system. When I talk about these kinds of small bodies, I'm thinking icy moons of Jupiter, Saturn, Uranus, Neptune, thinking about distant objects in our solar system, the dwarf planets like Pluto, Sedna, and these other trans-Neptunian objects. Well, when we look at those objects, we see clear chemical differentiation of the surface ices. Now, this can happen for various reasons. Geological processes, for example. If we look to the very small moons of Uranus, which may be hundreds of kilometers across, they're big enough that when they formed, in the protoplanetary disk or in their subnebular part of the formation zone where they formed, then it's quite likely that they have a differentiated chemical structure, which means that some ices may sort of float to the surface. The heavy elements, the metals, sink to the core. They're warm enough that these kinds of bulk transport processes can happen, and you end up with a differentiated object. Typically, comets aren't considered to be large enough to be able to do much of that. They don't get hot enough when they form. When they form, they don't preserve enough of the formation energy, the heat. It gets radiated away. So they're pretty cold. But we can envisage comets forming in different parts of the protoplanetary disk that they came from. There could be a water-rich part of the disk where there's a lot of icy pebbles, maybe closer to the sun, and more carbon dioxide, carbon monoxide, methane-rich as you go further out. So we can form different bodies in these different parts of the protoplanetary disk through mixing processes, through gravitational and dynamical mixing of these bodies throughout the disk. They can be transported in or out, and maybe two chemically different objects can meet each other, come together in a slow collision, and ultimately coalesce into a single object that may have a differentiated composition. So we may be able to probe these kinds of dynamical and chemical processes if we observe dramatic changes in the chemical composition that can't be explained in other ways.
A lot of options there, and I think one of the things that speaks to that is, you look at these outer solar system objects, and we looked at the one with New Horizons, that it's two objects coalescing very slowly. They come into contact, they're orbiting each other, and then they come into contact. Well, what does that do to composition? Now, one of the interesting aspects of 3I Atlas is that we see nickel chemistry, and we see evidence of that. Not really seeing iron, and those two like to go together. What do you think about that mysterious aspect of this object?
So yeah, you're talking about some observations which were done with the VLT telescope, spectroscopic observations of 3I Atlas in the sort of optical UV range. I'm aware of those, and I saw the spectrum there, and I saw so many peaks in the spectrum due to nickel, just atomic nickel. Now, the detection of these kinds of atomic metals in our own comets from our own solar system was only first realized a few years ago, maybe in the last 5 or 10 years, that comets contain these atomic metal vapors. And to my knowledge, since their discovery, it hasn't been possible to explain why comets contain those metallic vapors. So this is a really interesting puzzle, and I was very intrigued to see detections of iron and nickel in the second interstellar object, 2I Borisov. It implied that it was subject to a similar sort of maybe surprising metal-based chemical composition for some of the material inside that object. Now we're seeing 3I Atlas, very nickel-rich. No apparent signatures from iron vapor. Iron and nickel are both produced inside massive stars late on in their lives. And, we're thinking about whether this object, 3I Atlas, may have originated from a metal-poor system, an old star, which maybe there was lower enrichments of metals in its surrounding protoplanetary disk when it formed. It seems plausible that 3I Atlas could have formed in a relatively low metal environment, and yet we're seeing a strong nickel signature. So chemically, that's very interesting. And from an elemental synthesis perspective, from understanding how atomic elements become created and these sorts of heavy metal atoms get produced in the galaxy, I think that this is probably going to be telling us something pretty interesting about the nature of the material this object formed from. I would say it's too early yet to really be definitive, because we're observing this object quite far from the sun. We've talked about the issues pertaining to how different ices and substances enter the gas phase and sublimate as the comet comes closer. Potentially the iron could start to appear. I would say it's early days to say for sure this object is iron poor. So once we have more observations in hand, we'll be able to make a more robust statement about that, and then try to understand more about whether that is indeed a signature of a peculiar initial elemental composition, and what that could therefore mean in the context of how these elements are synthesized and enriched within our galaxy, and what their initial compositions may have been. So yeah, I think it's a fascinating question. I think it's really fascinating to try to understand why we're seeing these metal vapors in the comet coma as well. It's not obvious, mainly because these kinds of metals, they typically, when we think of how interstellar chemistry works and how dust chemistry works, everybody knows that metals like to stay in a solid form. If you were going to make something to survive a fire, would you make it out of ice or wood or or metal? It's pretty obvious, right? And so these kinds of metals, these metallic atoms, they like to stick together. They like to form metals. They like to be solid. Why are they sublimating into the gas in a comet coma, coming out of essentially an icy phase, a very cold phase associated with a lot of ice? This is something very peculiar, and it's a great question for chemists to try to answer. It seems as though these metal atoms are probably bonded in some kind of chemical structure that is liberated during sublimation, along with the ices that are sublimating. Yeah, as I say, something for the chemists to go after in the lab and try to explain this.
That's a huge chemistry question. It's really interesting because you're looking at, ostensibly, again, early chemistry for the universe. So things might have been a little bit different back then, especially if it's really, really old. And that might hint at certain things. Now, with meteorites, we see obviously tons of nickel and iron in our meteorite collections. And this is sort of saying, well, it's a little bit different when you're forming way out far from your star. And, we see that too with the carbonaceous chondrites, and that those metals drop off. Those are associated with comets or cometary material, and those metals start dropping off, but they're still there. But they're still at that same ratio of typically 7% nickel and most of the rest iron. But without an iron emission here, it's a little bit weird. Is it possible, though, that we know that asteroids differentiate? We have pallasites, which are kind of borderline between chondrites and iron meteorites, and then, iron meteorites but comets really don't. And so does that speak to where this object formed in its star system of origin? Did this form someplace likely to be very, very cold, like our Oort cloud? Or could it have formed a little bit closer, and that's the weirdness? That might explain some of the weirdness.
Yeah, so there's a lot of questions there about asteroid chemical abundances and how those come about. As you rightly said, asteroids can be differentiated. They may have come from larger bodies, which were able to thermally differentiate. For the comets that formed in our solar system, the presence of very volatile, hypervolatile ices, methane and carbon monoxide, they show us that our own comets must have formed, or must be comprised of material that formed at these extremely low temperatures. And even N2 was molecular nitrogen was detected in comet 67P by the Rosetta mission. It's incredibly volatile. That won't stay around through any sort of thermal processing. So I don't envisage that our own comets have been subject to much in the way of thermal processing. They do incorporate grains from the Stardust mission, where cometary dust grains were collected and brought back to Earth in a special kind of gel that captured those grains and brought them back intact.
Yeah, the aerogel, where everybody was citizen scientists and looking for tiny grains embedded in the aerogel from that mission. It's absolutely amazing.
Yeah, it was incredible that so many of those grains were detected, and a lot of the organics got burnt off, but I think a decent amount of the metals were remaining. Those grains that were picked up within the aerogel were found to contain minerals, olivines, iron-rich silicates that were formed. They can only be formed at very high temperatures. And so what this tells us is that comets can contain materials that were formed at high temperatures, but those grains where, they're small, and we're not talking about macroscopic particles here. We're talking about microscopic particles, sort of microns in size. And those kinds of grains, which are present in comets, clearly contain these metallic substances that we're talking about. So they can certainly be incorporated in comets. But the actual chemistry of those and how they can lead to the production of just atomic vapor upon sublimation, to me, that's still a significant puzzle.
Now, regarding the brightness of 3I Atlas that we briefly touched on, it's unusually bright for what it is. That's not really saying much. You're not going to walk outside and see this thing unless you've got a 8-inch telescope or something like that. But it is bright, and that's leading to the ambiguity of the size, which Hubble constrained that down. I think you said 2.5 kilometers, something like that, which is actually really small compared to something like Comet Halley or something like that, which I think was orders of magnitude larger. So
Halley was about 10 kilometers.
Yeah, it was bigger than, it was like 4 times that size. So this is a small object, but that's not all that well constrained. And some people have said that if the object actually turns out to be really large, which, the upper limit on that was like 24 kilometers in early July, but I think that's not on good, solid ground at this point. But that would make it very, very strange. Is there anything about this object that gives you pause? And other than the chemistry, which is interesting in its own right, but it's not unexplainable. Is there anything that gives you pause, given the controversy that surrounds this object, that makes you go, that's a little too weird? Or is it well within the limits of what you would expect from an interstellar comet, accounting for what we don't yet know about these things?
Yeah, so great question. And there's a lot that's weird about this object. Is there anything that's too weird to be explainable as a result of natural phenomena? I don't think so. But from what we know about the orbit, the trajectory of this object, it's a little unexpected, to the point where we would say it's on a statistically unlikely trajectory through the solar system. And I want to give the dynamical modelers a lot of credit for what they've done in working out the potential paths of these objects through the galaxy. And there is a stronger likelihood of encountering these objects from certain directions of the sky as a result of the direction that our sun is moving through the galaxy, and also higher probabilities that these objects appear from certain constellations based on streams of these objects through the galaxy. They interact with gravitational fields and galactic tides, which push them about and form them into streams. And the Otautahi Oxford model was saying that this object seems to be a little surprising in terms of where it's coming from. It's coming from a direction away from the solar apex. So if you were just to pick an interstellar object at random, you would expect it to be coming from somewhere in the northern hemisphere of the celestial sphere. This one's coming from the south, coming from the direction of Sagittarius. And so just that origin, that point of origin is a little peculiar, but not to the point where I would say, that's statistically extremely unlikely. These objects can come from any direction in the sky. So the fact that one comes in from this direction and it's at an angle very close to the orientation of our ecliptic plane, the plane that the planets are orbiting. All our planets are orbiting in this plane of the solar system, and 3I Atlas is coming in at 5 degrees to that plane. So that in itself is also fairly unlikely for it to be on this trajectory that brings it so close to Mars and Earth's orbit, and then onwards out. It does a very close flyby of Jupiter later on as it's on its way out. So the actual trajectory of this object is a little bit unexpected, but as I say, not to the point where I suspect anything really strange going on, but that's just something notable, I think. Other peculiar things about this object that are noteworthy, in addition to the CO2-rich coma, the nickel-rich coma that we've already talked about. When it was discovered, and within a few weeks after the discovery, it was showing this ejection, or basically a sunward enhancement in the coma, which means that the coma dust seemed to be having a tendency to to show an asymmetry in the direction towards the sun. And because this object is coming in on a trajectory through our solar system that goes pretty close to the sun, then that means that the direction, if you're standing on the comet nucleus, standing looking up at the sun, the direction you'd be looking up in would be similar to the direction of travel of the comet. And that's the direction that it seems to be preferentially producing its coma in, or at least it was. The latest images from the Gemini telescope were showing that, contrary to those initial images from early on in its detection, it's now showing a tail or trail of debris that is more typical for a normal comet and pointing in the direction away from the sun. So it's behaving a bit more like a normal comet now. And, we may sort of think to ourselves that that was a very peculiar thing to observe a comet with a tail pointing towards the sun. But as I say, we think of it more like a plume. And when you think of it like a plume, it's not altogether surprising to envisage a situation where the nucleus of the object is heating up on this direction towards the sun. That's where the sun rays are striking and warming the surface. And that's where the production of gas is likely to be the strongest, driving out the dust in the direction towards the sun. And imagine this object hasn't been exposed to any heating for perhaps billions of years. The first thing that happens when it starts to heat up is you might start to get some outbursting kind of events as pressure builds up beneath the surface. You may get some sort of violent ejections of dust during those initial warm-up stages of this object that could force out the gas and dust in the direction towards the sun. So from that perspective, yeah, it's an interesting object. It comes from a slightly weird place, and it was doing some slightly weird, unexpected and unusual things when we saw it. But I don't think it's surprising that an object from such a different part of the galaxy potentially would behave in a slightly unusual way when it first starts to get heated up.
It's interesting about the sun spike or anti-tail, whatever you want to call it, but I'm careful with that because comets actually have two ways to produce an apparent anti-tail. One is, preferential heating you're talking about, where it's shooting it off in one direction. But also, you can get an optical effect or a perspective effect of anti-tails with comets. And I actually saw that with Hale-Bopp. So you've got two mechanisms, and it's like, well, interesting, but I don't know if too much should be made of it. However, what I want to hammer home here is on the point of it coming in from a slightly weird angle, that could get way weirder. And if we'd have had all these spacecraft during, for example, the Grand Tour alignment that we took advantage of with Voyager 1 and 2, and you see it, some kind of an object coming in and doing very close passes like a Voyager spacecraft to as many planets as it can based on where it's coming from, this could get much, much stranger, is my point, that you could see something that would really raise eyebrows, based on alignments of the solar system. If somebody were to, some alien civilization wanted to take a look at everything here, you could do much better than this and pass much closer to planets based on alignments. And I think that it's not hard to point a telescope to the solar system and work out what the orbits of these planets do. We do that ourselves. So it isn't that far out of normal. But I have one final question for you. Should we even be calling this a comet, or should we be calling it an exocomet? A burning nomenclature question for you, and I worry about such things. Should we be calling this the exocomet? And should we have an entirely different, well, I know we have the I, 3I, 2I, whatever, but should we change our terminology regarding this object?
Yeah, I like that idea, actually. It's awkward for me to always talk about comparing this comet to the comets from our own solar system. And that is to say that, there needs to be a way to talk about this thing in the context of comets, maybe without actually calling it a comet. It's nice to reserve the word comet for our own comets, right? Which we've been studying for, well, thousands of years. If you look into the historical records, comets have fascinated astronomers over the eons, and we've learned a lot about them and their chemistry in the last few hundred years. So yeah, to be able to to really discuss these new objects and give them the credit they deserve compared to our own comets. I would probably say that calling them exocomets is reasonable. There's a field of study already in place which studies exocomets in protoplanetary disks or debris disks around young stars, where we believe dust and gas is coming together to form new planetary systems, and we see signatures of outgassing bodies, which are what we have referred to as exocomets, because the analogy is with exoplanets, right? Exoplanets are planets around other stars. Exocomets have therefore historically, that's the term coined for comets around other stars. Well, interstellar comet seems like a pretty good moniker for these kinds of things, because they've spent most of their lives in the interstellar medium. So I quite like interstellar comet. Exocomet could do.
Or you could say former exocomet. It's interesting because, I remember papers from a number of years ago now that had looked at the Kepler data and detected what appeared to have been exocomets, as you said, in young star systems moving through. And they actually had a certain very specific profile. It was really interesting. But my question would be is that as you get better observational ability, say you build a super Kepler spacecraft, could you work out if that comet passing by the another star, could you determine if it's interstellar, moving through another star system at a hyperbolic orbit? But I don't think anybody's thought that far ahead. Doctor, thank you for joining us today, and I wish you great luck in continuing to study this object. And I'm making the popcorn, so to speak, to look at the chemistry of this object and how that evolves as it passes through the star system.
Thanks a lot, John. Yeah, we've still got a lot of work to do.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.